Hi, this is the fourth video in this little video series on the matrix groups SO2 and O2, the second special orthogonal group and the second orthogonal group. And in the last video, we worked rather laboriously through the proof, pretty good proof, pretty watertight, maybe a few little things left for you to fill out here and there. But the proof that SO2 really is a group, that these rotation matrices really do form a group. And so what I want to convince you of in this video is that you can, in some sense, think of this group, this rotation group of rotation matrices as being the same as the unit circle, which we call S1. So this is what the goal is: convince you that SO2 is somehow the same as the circle S1. I guess I will not leave out any words. I'll say unit circle, although you could identify it with any other circle you wanted as well. It doesn't really matter what size it is, but we'll just be specific and say the unit circle. Unit circle S1. Now, what does this "the same as" mean? Well, here's what it means. I'm going to draw a dividing line here, and I'll say it informally. I say you give me an angle, well, you give me a point on the unit circle, and I give you a rotation matrix. So we can go that way, or we can start over here and we can say you give me a rotation matrix and I can give you a point on S1. Now, it's not good enough for just one of these to work. For me to, to start out with a point on S1 and be able to get a rotation matrix, it's not even good enough for both of them to work, where you start out with a rotation matrix and you get a point on the unit circle. What has to happen is that when you do this and you start with a point here on S1, go to a rotation matrix, then if that's the rotation matrix you give me, it has to come back to be the same point. These will have to come back to be the same point on the unit circle. So the idea of this is, and vice versa. I mean, you could start here, go this way, and then go this way, and these would have to come out to be the same here. And so what that means is that you don't lose any information when you go from a point on the circle to a rotation matrix, or vice versa. You don't lose any information. You can go back to where you were. You can get back home. You don't destroy any information by doing that. And the same here. If you start with a rotation matrix and you figure out a point on the unit circle from that, you can use that point on the unit circle to reconstruct the rotation matrix. It doesn't destroy any of the information involved. So this is the idea here. Now, so when this happens, then it means that you can identify the two structures as being somehow the same. So we're going to imagine that the donkey here, gives me, it's like he can only see the rotation matrices, right? And I can only see the unit circle. It's like we're both very stubborn about how we insist on viewing the same structure. And so the idea is that either his point of view or my point of view is equally valid and contains all of the same information as the other. There's neither point of view is better than the other, and you can get from one point of view to the other. And so that's what the identification means. And it's, I don't know, you could say like, SO2 says, I was born a matrix group, but I identify as a circle or something. No, actually that's different, because in that case, you would be having things that were essentially different in some sense. These are entirely the same. There's no way you can tell the difference between them whatsoever. All right. So I want to convince you that SO2 is the same as the unit circle. How are we going to do it? Well, let me draw the unit circle over here. It's maybe not the best unit circle I've ever drawn, but it will do. And so this is S1. S, by the way, stands for sphere in general, and 1 stands for one-dimensional. For instance, S2 would be the two-dimensional sphere that you're used to. And then it's fun to think what S3 is. And you know, later when we talk about some other matrix groups like SO3 and SU2 and so on, if we get to these, then these are related to S3 in some way. So you can't visualize it as easily as you can S1 and S2, that's for sure. So that's on this side. And then over on this side, we want a matrix group, a rotation matrix. So the game we're supposed to play is I tell you a point on the unit circle, and you're supposed to tell me a matrix. And so that means you have to tell me 4 entries. Now the way you do this is, so there's this point here, and you can draw the line segment from the origin to this point here, and that has an angle theta, we'll call it theta, with the x-axis. I could call this x-axis, this the y-axis. Now notice that all comes from this point. Given this point, I can always do that. That's fine. And then I can take this distance here will be cosine theta. That distance there will be sine theta. My x is kind of in the way a little bit. And then so given this point here, I can get a cosine and a sine. And then what can I do? Well, I can proceed to build a rotation matrix, which is that one there. Cosine theta minus sine theta, sine theta, cosine theta. So I've gone from this point on the circle and I've gotten a rotation matrix. Now it's unique. There's no ambiguity in what that angle is. It's this particular one here. Now that's if I choose, you notice that there is an arbitrary choice in here, I guess, which is that you're choosing to start rotating from the positive x-axis. I mean, if I chose to rotate from this axis, then I'd get a different angle. But the point is you can always choose a place to start. Here we're going to choose the positive x-axis, rotate that way, and we get a unique answer once we've chosen a place to start. Now, if we go back the other way, well, this is pretty obvious. I'll call the angle a different angle. Say I call it phi now. Cosine phi minus sine phi, sine phi, cosine phi. This is a rotation matrix. Any rotation matrix can be written that way. Any two-dimensional one, that is. And so, given that, and I guess I've drawn my unit circle too big over here, what I can do, let me just partially erase this. What I can do is I can start drawing. I can draw the plane. I can draw the unit circle in the plane. I can start at the positive x-axis. I can rotate by angle. Maybe this is some bigger angle, for instance. I can rotate by an angle here. I'm not going to draw an arrow there, I don't need it. But I can rotate by this angle, whatever that angle is that I'm given, this angle phi, and that will choose out a point on the circle, namely the point that is the intersection of this line given by rotating the x-axis up to angle phi, the intersection of that line and the unit circle. So here I went from a point on the circle to a rotation matrix. Here I went from a rotation matrix to a point on the circle. Now I think it's pretty obvious that if I start with this point on the circle and I get this rotation matrix, then if I started with this same rotation matrix, I mean if I did say, well, let it be that same angle, so if I put a theta here, theta, 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 well then I think it's pretty obvious, and let me go back over here. I think it's pretty obvious, well, I'd be rotating by that same angle there, the same one we have here, theta. And so I'm going to get, and you know, that this is the same distances here, although I don't have to redraw the whole thing, I guess, but I guess I am doing it. That's sine theta. It's pretty obvious I would get the same point. So it's an invertible process. It's something I can reverse. It's something where I don't lose any information. I go from here to here, I use that same one, go backwards, I get to the same point. And similarly, if I start with this matrix here, send it over, get this point, if I use that same point to construct a rotation matrix, it will be the same one. So this shows you that you can think about the circle group, not the circle group, well, it is the circle group. That's another way of saying it, but you can think about the group SO2 as being identified with the unit circle. Now, I hope I have convinced you of that. That was the goal. So let's assume that I have, and if not, you can rewatch that part. But so this is, I want to make a couple of remarks about this. So remarks, this S1, it has a geometric structure. And you're familiar with this. I mean, it's the point, it's the locus of all points in the plane. You can write this as all points in the plane x and y such that x squared plus y squared equals 1. You can think of it in a geometric way. Now, this kind of continuing the same way, S1 is a manifold. It's what's called a manifold. And so what a manifold, what this means is that it looks locally like Euclidean space. And so what does Euclidean space mean? Well, in this case, the Euclidean space is just the real line, R. In general, it could be, and we could say R1 for one-dimensional, and then the plane would be R2. I'll just write this briefly and then erase it. The plane would be R2. Ordinary space that you think of would be, I wrote R3 there, I mean R2. Ordinary space would be R3. You know, the ordinary space you think of, although it's really not structured that way. So what manifold means is that it looks locally like that. And what does locally mean? Well, let me take this off. What it means is that if I take the unit circle, let me just draw it here without drawing the coordinates on it, and I look near a point here and I zoom in. So let's say that I zoom in on this here, near that point there. Well, then it starts to look, it's almost like a line. So this is almost like the real line here. And so, I mean, you can imagine that if I zoomed in even closer, like say I take really close to this and then I zoom in again, so now I'm kind of messing this up. but you can imagine that near that point, this would be almost straight. It would be nearly like, it would look nearly like the real line. And so, anyway, I don't know if you appreciate my artwork here, but you can imagine taking that circle and looking at it under a microscope, and as you get closer and closer, you are less likely to see the curvature. It's not unlike the way it is being on the surface of the Earth, that you don't notice the curvature because the Earth is so large. You're zoomed in, whereas if you zoom out in space, then you can see the curvature easily. So S1 is a manifold. Let me take off this this thing here. And it's, in fact, what's called, and I'm repeating myself with the S1, S1, S1 here, but just to be clear, it is what's called a Lie group. It's a Lie group, and this means that it has both group structure. I guess I didn't make my parentheses big enough. Both group and manifold structure. And there are a number of different ways in which you can see or understand this structure. One more remark I'll make, and then we'll call it quits with this particular video. S1, it can also be identified with the unitary group U1. Now, I haven't told you about unitary groups, but we may talk about it at some later point, and you can always look at it, if you want to. And so this is another way, using complex numbers, of understanding the circle. And this is essentially what you're doing, is you're looking at theta, and you're comparing this to e to the I theta. And we'll actually talk about this idea a little bit in the next video. The idea of covering the SO2, the circle group, you can think of it as by the real line, whatever that means. But in this video, I just wanted to show you, if you're given a point on the circle, you can get a rotation matrix. If you're given a rotation matrix, you can get a point on the circle, and the two operations are inverses of each other. You'll get back to where you started, going either way. And then all this stuff is interesting, but manifolds, that's differential geometry stuff, and I'm of course not assuming that you know that, but it's worth mentioning anyway. So we have checked this off, and next we'll talk about a relationship between the real line and the special orthogonal group SO2.